Driven by market needs and environmental legislation, mechanical engineers develop new prototypes lighter and more flexible. This is, for example, the case in aerospace engineering, for instance with a Solar Impulse that features wider wings than the Boeing 747, but has the same weight as a car. The introduction of flexible elements, such as the solar arrays of a satellite or the blades of an open rotor, may also involve large displacement and complicated dynamics at the interconnections. As a consequence, modern structures are more prone to operate beyond linear regimes of motion. They behave non-linearly. A peculiar feature of nonlinear structures is that, for the slight variation of a parameter such as the airspeed or the excitation frequency, undesired vibration can be suddenly triggered. Let us consider the example of this glider. At lower speed, the wings do not vibrate. As the airspeed is increased, this equilibrium state turns unstable and fluid structure interactions generate limit cycle oscillations. This type of phenomenon is related to the presence of bifurcations in the system's response. Many examples of bifurcation can be found in aeroelastic systems such as bridges or aircraft. When a nonlinear structure is operating in a linear regime of motion, only one periodic response exists at a given excitation frequency. After a perturbation like a small impact or a wind gust, the system will recover the same response. At higher excitation levels, however, the activation of the nonlinearities will modify the shape of the frequency response and will create a bistable region. In this region, a low amplitude response may jump to a high amplitude vibration after a perturbation. Fault bifurcation set the boundaries of the bistable region. These bifurcations can be found near the nonlinear resonances, and they are responsible for the amplitude jumps. There also exists other types of bifurcation. At branch point bifurcations, for instance, an additional branch of periodic solution is created. The Neymer-Sacker bifurcations generate quasi-periodic oscillations with potentially higher amplitudes than the resonance peak itself. As the dynamical changes described previously may jeopardize the integrity of the structures, bifurcations certainly deserve a special attention. They should be considered by engineers in their numerical simulations and must be anticipated during test campaigns or experiments like here in the wind tunnel. Although industrial structures also suffer from adverse phenomena due to the presence of bifurcations, numerical methods to study bifurcations could only be applied on small-scale academic systems. In this context, my thesis developed a new computational framework intended to bridge the gap between bifurcation analysis and industrial applications. The starting point of my work was to select a formalism to compute nonlinear frequency responses and normal modes. In that regard, the harmonic balance method was the most suitable candidate. This technique consists in approximating the unknown periodic solutions of the equations of motion with Fourier series. The resulting algebraic equations to be solved do not require any time integration that could be costly. Moreover, the number of unknowns can be reduced by decreasing the order of the Fourier series approximation and hence neglecting higher harmonics that are usually damped out in experiments. For this reason, the harmonic balance method is very efficient for large-scale systems. My efforts were then devoted to extend the harmonic balance formalism to perform bifurcation analysis. In order to apply my tools on large finite element models while ensuring a limited computational burden, I developed a framework that builds on several techniques. These techniques are a continuation procedure to compute branches of periodic solution iteratively, the monitoring of test functions to detect and characterize bifurcations. Finally, a bifurcation is detected when a specific matrix, let's call it capital G, gets singular. Because dealing with matrix determinants may be difficult for large systems, And in order to avoid ill conditioning, I propose to use the bordering technique. The resolution of the border system provides a scalar, small g, that vanishes when the matrix capital G is singular. Let us now apply the proposed algorithm to compute the frequency response of a nonlinear system excited at 1.5 Newton. Along the frequency response, branch point bifurcations in red and fold bifurcations in orange are detected. Let us now imagine that we are interested in the evolution of this resonance peak as we increase the forcing amplitude. A trivial way to proceed would be to compute this frequency response at the value of 2 Newton. This way, however, we have to recompute all the portions of the frequency response. Some of them might be not necessarily interesting. Therefore, I propose an efficient adaptation of my framework to track bifurcation in the substance parameter space. Let us apply this technique on the fold bifurcation right there. Obviously, using this method, we are now able to really focus on the bifurcation and obtain the evolution of the resonance peak immediately. Applying this tracking procedure to the Neymark-Sacker bifurcations that appeared at 2 Newton, we are able to predict at which forcing amplitude these two bifurcations are created. An important step in the thesis was to demonstrate that the bifurcation detection and tracking methodology could be applied to industrial cases. To this end, I validated my developments on the numerical model of the SmallSat spacecraft. The SmallSat spacecraft was developed by Airbus Defence and Space and possesses an inertia wheel for attitude control. Elastomer plots and mechanical stops were introduced to mitigate micro-reverberations emanating from the wheel and large amplitude oscillation during launch. These connections feature linear piecewise stiffness curves due to the impacts with the stops, and thus involve nonlinear dynamics. First, simulations of swept-sign responses were performed on the nonlinear finite element model of the spacecraft at different forcing amplitudes. These simulations indicated the presence of quasi-periodic oscillations, but also a sudden shift in the resonance frequency of the sixth mode. With my research developments, I could then reveal the presence of Neymark-Sacker bifurcations near the quasi-periodic oscillation and of fold bifurcation near the resonance peak. Tracking this fold bifurcation highlighted the presence of an isolated response curve that expands as the forcing amplitude increases and finally merges with the main frequency response. This phenomenon, that had never been discussed in the literature for an industrial application, explained the frequency shift in the time series. Bifurcation tracking proved useful to understand the dynamics of the structure, but was also proposed for design purposes. By studying the influence of the damping introduced by the elastomer plots, I showed that the design of the structure could be optimized to eliminate the Neymark-Sacker bifurcations and thus the quasi-periodic oscillations. The efficiency and robustness of the framework I proposed motivated its implementation in the Ni2D software. This software has been developed in my lab to perform advanced vibration analysis of nonlinear structures from measurements data to design optimization. My contributions in this software for bifurcation analysis are currently being tested by industrial partners. Robert Kuether, working at the Sandia National Lab in the USA, is one of them.
My name is Robert Kuether, and I am a senior member of the technical staff at Sandia National Laboratories. Sandia is a research and development national laboratory for the United States government. The continuation and bifurcation tools that are implemented in the Ni2D software provide an excellent platform for Sandia engineers such as myself to use advanced analysis tools to better understand the nonlinear phenomena in vibration responses. I've used Ni2D continuation code to compute the nonlinear normal modes of nonlinear reduced order models, which helped serve as a convergence metric for models of varying fidelity.
The tools I developed during my thesis and their validation on large-scale models and by industrial partners show that advanced study of nonlinear vibrations and bifurcation analysis can now be performed by engineers. I thank you for watching.